All right, so we're diving deep today, getting into some really interesting math, specifically sectors and segments of circles. We've got some great material from a textbook here, and I'm excited to break it down, really understand these shapes. And who knows, maybe we'll even find some surprising ways they connect to, like, our everyday lives.
Yeah, definitely. It's amazing how these seemingly simple shapes can be so useful. And you're right, they do pop up in unexpected places. It's all about understanding how to quantify those parts of circles.
Oh, exactly, exactly. Okay, so let's start with the basics. What exactly is a sector?
Well, think of it this way. You know how when you cut a pizza, you get those triangular slices.
Yeah.
Each of those is a sector. It's that portion of the circle, that's enclosed by two of those straight lines coming from the center, the radii,
Right, right, the radii.
and that curved part of the crest, the arc.
Okay, so like two radii and an arc. That makes a sector.
Right, exactly. And you can have, the smaller slice, a minor sector, or a bigger one, a major sector, depending on, well, how big of a slice you cut.
Like in figure 11.1, we see both, right? We have OAPB, which is the smaller sector, and OAQB, that's the bigger piece.
Exactly. And the way we tell them apart is by that central angle.
Right, right. The angle formed at the center of the circle by those two radii.
Yeah. So for the minor sector, OAPB, we have that angle AOB. And for the bigger one, it's just the rest of the circle. So 360 degrees, the whole circle, minus that smaller angle AOB.
Makes sense. So sectors, that's our pizza slices. What about segments then? How are those different?
Okay, so for segments, imagine instead of cutting from the center to the edge, you just cut straight across the pizza.
Okay.
So you draw a line, a chord, connecting any 2 points on the circle.
Sure, right, right.
And that, along with the arc between those points, that makes up a segment.
Okay, so like in figure 11.2, we have APB, that's the smaller segment, and then AQB, the bigger one.
Right. And just like with sectors, you have minor segments and major segments.
And I noticed the text says, unless we specifically say minor or major, we're usually talking about the smaller one.
Yeah, that's just a convention to simplify things.
Okay, good to know. So we've got a picture in our minds now of what sectors and segments are, but how do we actually measure them? Like, how do we calculate their area?
All right, so let's start with sectors. Remember, the area of a whole circle is pi r squared.
Right, pi r squared, that classic formula.
Yeah, and that represents, well, the whole 360 degrees of the circle. So to find the area of just a sector, we need to figure out what proportion of that whole circle it represents.
Okay, I think I see where you're going with this.
So say our sector has a central angle of, let's call it theta. We can think of it like this. If 360 degrees equals pi r squared, then 1 degree would represent just a tiny fraction of that area.
Right, so you divide the whole area, pi r squared, by 360.
Exactly. And if our sector has an angle of theta degrees, its area would be theta times that tiny fraction.
Okay, so the formula becomes theta over 360 multiplied by pi r squared. Makes sense. It's like taking that proportion of the whole pi, as you said.
Precisely. And the same logic applies to finding the length of that curved edge of the sector, the arc.
Oh, right, because the whole circumference of the circle, that's 2 pi r.
Yeah, so the length of the arc of a sector, that's just theta over 360 multiplied by 2 pi r.
Got it. So we have our formulas for sectors. Now, segments look a bit trickier, right? Because they have that straight edge, the chord. How do we figure out their area?
Well, the good news is we can use what we already know about sectors and triangles to help us here.
Okay, how so?
So look at figure 11.4. See how the segment is basically a sector with a triangle cut out of it.
Ah, I see, I see.
So to find the area of the segment, we take the area of the whole sector and then subtract the area of that triangle.
Okay, that's pretty clever, actually, breaking it down like that.
Right. So for the minor segment APB, for example, we take the area of sector OAPB and subtract the area of triangle OAB.
So 2 steps. First, find the sector area, which we already know how to do. And then second, figure out the area of the triangle.
Yeah. And that second part, finding the triangle's area, that's where we might need some extra tools depending on what information we have. Sometimes it might be a simple case of half base times height.
Right, the classic triangle formula.
Exactly. But in other cases, we might need to use some trigonometry. But that's a whole other deep dive.
Maybe for another episode.
Yeah.
Okay, so back to segments. The text also mentions a helpful way to deal with major segments and sectors.
Oh, you mean the idea that you can find the area of the major part by subtracting the minor part from the whole circle.
Yeah, exactly. So instead of dealing with that big angle for the major sector, we can just use the smaller angle and subtract from the whole circle's area.
Right, right. That can definitely save some time and effort.
Okay, so we've got the concepts and the formulas. How about we put them into practice with some actual examples?
Yeah, let's do it. That's always
Mhm.
the best way to solidify our understanding.
All right, so example one. We've got a sector with a radius of 4 centimeters, and the central angle is 30 degrees. We need to find the areas of both the minor sector and the major sector, and we're using pi as approximately 3.14.
Okay, so for the minor sector, we plug our values into the formula. Area equals theta over 360 times pi r squared. So that's 30 over 360 times 3.14 times 4 centimeters squared.
Which, if we simplify, is 112 times 3.14 times 16 square centimeters.
Yeah, and that comes out to about 4.19 square centimeters.
Okay, so a little over 4 square centimeters for that slice. Now, for the major sector, we could go about it in two ways. We could calculate it directly using the major angle, which is 360 minus 30. That's 330 degrees.
Or, as the text suggests, we could just subtract the area of the minor sector from the total area of the circle.
Right, so the total area is pi r squared, which is 3.14 times 4 centimeters squared. That's 50.24 square centimeter.
And then subtract the minor sector's area, 4.19, and we get 46.05 square centimeters.
And just to confirm, if we do it the other way, using the major angle of 330 degrees and plugging it into the formula, we should get the same answer, right?
Absolutely. Let's check. 330 over 360 times 3.14 times 16 square centimeters. And yep, that also comes out to approximately 46.05 square centimeters.
Terrific, the numbers match up. Okay, on to example two, which is about finding the area of a segment. And this one, well, this one looks a bit more challenging.
Yeah, it involves a couple more steps, but remember, we can break it down.
Right. So we have a radius of 21 centimeters, and the central angle AOB is 120 degrees. This time we're using pi equals 227.
Okay, so first we find the area of the sector, OAYB. That's 120 over 360 times 227 times 21 centimeters squared.
Which simplifies to 13 times 227 times 462 square centimeters for the sector's area.
All right, first part done. Now for that triangle, OAB.
Right, and here's where we need to visualize things a bit. The text talks about drawing a line from the center of the circle, O, perpendicular to the chord AB. They call that line OM. Okay, so OM basically splits that triangle OAB into two right-angled triangles.
Exactly. And since OA and OB are both radii of the circle, they're equal in length, which means triangle OAB is an isosceles triangle.
Right, two equal sides. And since OM cuts AB at a right angle and the triangle is isosceles, it also means OM cuts that angle AOB in half.
Precisely. So each of those smaller angles, AOM and BO, they're half of 120 degrees, which is 60 degrees.
So we've got two right-angled triangles, and we know one angle is 60 degrees. That means we can use trigonometry to find the lengths of the sides.
All right, so in triangle OMA, we have cosine of 60 degrees equals OM over OA. That means the length of OM, which is also the height of our triangle OAB, is OA times cosine 60.
So 21 centimeters, the radius, times cosine of 60, which is 12.
And that gives us 10.5 centimeters for OM.
Okay, great. Now what about the base of the triangle AB?
We can use sine for that. In the same triangle, OMA, sine of 60 degrees equals AM over OA. So AM, which is half the base of our triangle, is OA times sine of 60.
So 21 centimeters times sine of 60, which is root 3 over 2.
Which means the full base, AB, is twice that length. So 21 times root 3 centimeters.
Okay, awesome. We have the base and the height of the triangle. So its area is 12 times base times height.
Which means 12 times 21 root 3 centimeters times 10.5 centimeters.
And that comes out to, let me see, 441 root 3 over 4 square centimeters.
Right. And finally, to get the area of the segment, AYB, we subtract the triangle's area from the sector's area.
So 462 minus 441 root 3 over 4 square centimeters.
Exactly. And, if you want to be fancy, the text simplifies that to 21 over 4 times 88 minus 21 root 3 square centimeters. But the important part is understanding the process, how we use the simpler shapes to find the area of this more complex one.
Yeah, it's like solving a puzzle, breaking it down into smaller, manageable pieces.
Exactly.
But, this might all seem pretty abstract, but the exercises in the text in exercise 11.1, they show just how relevant these concepts are in real life.
Absolutely. I mean, think about question 3, the one about the area swept by a clock's minute hand. That's a sector problem.
Right, the length of the hand is the radius, and the angle it moves through is our theta.
And question 8, the grazing area of a horse tied to a corner of a field.
Yeah, the rope is the radius, and because the horse is tied to a corner, it can only graze in a quarter of a circle, so the angle is 90 degrees. And you can see how the length of that rope, the radius, directly affects how much area the horse can graze.
It's a direct application of what we've been talking about.
Yeah.
And there are even more complex examples, like the design of a brooch in Figure 11.9, which uses multiple sectors, or the area between the ribs of an umbrella in Figure 11.10.
It's amazing how these ideas are all around us. Even the area cleaned by car wipers, or the warning area of a lighthouse, as mentioned in question 12.
Yeah, that lighthouse one is a great example. The sector of light it casts, that's all about the radius, how far the light reaches, and the angle it sweeps through.
Right. A wider angle means a bigger warning area for ships. And in question 13, the one about the cost of designs on a table cover, figure 11.11, it looks like those designs involve segments of circles. So knowing how to calculate their area would be essential for figuring out how much material is needed, and therefore the cost.
Exactly. It all comes down to these fundamental geometric concepts.
So to sum it all up for our listener, the key takeaways are: for a sector with radius r and central angle theta, the area is theta over 360 times pi r squared.
And the length of the arc is theta over 360 times 2 pi r.
And for a segment, we find its area by taking the area of the corresponding sector and subtracting the area of the triangle formed by the radii in the chord.
It's all about understanding these building blocks of geometry, these simple shapes, and how we can use them to analyze and quantify the world around us.
Right. So, as we wrap up our deep dive into sectors and segments, it's clear that these ideas are not just abstract math, they're practical tools with a surprising range of applications.
Yeah, it's a great reminder that even the most basic geometric shapes can have far-reaching implications.
And on that note, I have a final thought for you, dear listener. Think about that horse grazing problem. How would changing the length of the rope, the radius, change the area the horse can graze?
Right. Remember, the area depends on the square of the radius. So even a small change in the radius can have a much bigger effect on the area.
Exactly. So what does that tell us about maximizing or minimizing circular areas in real-life situations? Where we might have limits on the radius. Or, going back to that lighthouse example, think about how crucial it is to accurately calculate that sector of light to ensure maritime safety and prevent accidents. These are just a couple of ways these geometric principles play out in the real world. And we encourage you to keep exploring these ideas, look around, and see where else you can spot sectors and segments in action.
It's all about connecting these concepts to the world we live in.
And with that, we conclude our deep dive. Thanks for joining us.
Until next time.